Hello everyone, let's solve today's problem of the day from Leetcode, maximum depth of binary tree. Let's read the problem statement. Given the root of a binary tree, return its maximum depth. A binary tree's maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. Alright. Root, this is the tree, the output is 3. How? This 3, 20, 15, 327. This is the maximum depth. Okay, let's try to understand. This is our binary tree. We are supposed to return the height of the maximum depth or height of the binary tree. So what is the maximum depth? If you see the tree, you can directly tell that this is the maximum depth, isn't it? But not this, right? So this height is what we are supposed to return. Okay, so how are we going to do this problem? See, we are given a tree and we are supposed to find the maximum height, right? For that we will have to reach the bottom of the tree, isn't it? So that is nothing but tree traversal. So how can we do a tree traversal? We can either use recursion or we can do an iterative approach, that is nothing but level order. So we will do both of them. We will try both the approaches. If you are watching this video, I will definitely expect you to have a basic knowledge of what tree traversals are and how they are done. Okay, so we will first do a level order traversal. We will go level by level, and as long as we are able to discover the level, we will be incrementing our height. Say initially we have the height 0. We have found a node here. We will increment the height. Then we will come here. We will reach this level. We will increment the height. Then we will reach this level. We will increment the height. After that, we won't be able to move any further. So that's where we stop, and our maximum height would be 3. Let's code this approach first. So we are supposed to return a height, right? So we will initialize a variable height. Okay, our nodes can be in the range 0 to 10 power 4. So there might be a case that we don't have any nodes in our tree, right? So let's put a condition for that. If root is equals to null, that means we don't have any node. So in that case, return 0 or return height, because it's initialized to 0. Otherwise, we will move further. Now we are going to perform a level order traversal, right? That is nothing but a BFS on a binary tree. So for that, we will need a queue of tree node, queue equals to new linked list, and initially we are going to put our root node into the queue. Now let's quickly perform our level order traversal. So this is the very standard and most common and basic way of doing a tree traversal. Okay, what we have done here is that as long as we are able to reach new levels, we will increment the height. Say this is 3, this is level 1. We have reached here, means we have level 1, that means height is 1. Alright, then we will move to this level 9 and 20. We are able to reach this level, means we have one more height, our height increases. Then we move further, we have 15 and 7. This is our last level. Our height becomes 2 plus 1, that is 3. We can't move further, so 3 is our answer. Let's dry run this code. So our height is now 0, and at the beginning we had put the root node, that is 3, into the queue, right? That means we are starting from level 1 now. So increment the height. Height is 1. Yes, height is 1. We are at the first level. Okay, now let's pull this out of the queue. Now we will see if children of this node 3 exists or not. We'll check if the left child exists. Yes, it exists. We will put this into the queue. The right child exists. Yes, it exists. We'll put this into the queue. Okay, so our first level, the work at our first level is done. Now we'll come here again. Okay, now we are at this level. Now when we are at this level, we will increase our height. We are at second level now, right? Then one by one we will pull these nodes out of the tree. Is there any child of 9? No, there isn't. Work done. Pull out 20. Is there any child of 20? Yes. What is the left child? 15. What is the right child? 7. We added them to the queue. Done. Our work at this level, level 2, is done. Okay. Now we will move to level 3. Now when we are at level 3, we are beginning afresh. At this level, we will increase our height again. Okay. Now let's pull out 15. Do you have any children for 15? No. Do you have any? We will pull out 7. Do you have any children for 7? No, we don't. So this is where it ends. So finally our queue is finally all empty and our iteration will stop, and then we will return the height. I hope that's pretty clear. The time complexity of this solution will be O of n. N is the number of nodes in the tree, and the space complexity will be O of n. We are at max storing all the nodes in our queue. So this is our level order traversal. Let's see one more example before moving to the next approach. Say this is our tree. I just extended the previous tree to this one. Okay, so initially we will have 3, that is the root node in our queue. Now we are at the first level. We will increase our height to 1, right? Now we will pull this 3 out of the queue and we will check for its children. The left child exists? Yes. The right exists? Yes. Fine. Our work at the very first level is complete. Now we are at level 2. Now as we have reached our new level, let's increase our height. Fine. Now let's pull this out of the queue. 9. Do you have any children? Yes, I have. I have a 4 at my left. At right, I have none. Done. Does 20 have any children? Yes. 20, we pull this out. 20 has a 15 in its left as its left child and a 7 in its right child, right? Fine. Now we are done iterating at our level 2. Now we will move to level 3. So as we have gained a height, we will increase our height. Done. Now at this level, pull out the first node, that is this one, 4. Hey 4, do you have any children? No, I don't. So get lost. What about 15? Let's pull out 15. 15 has a 8 in its left and a 2 in its right, isn't it? Fine, the work of 15 is done. Now let's check 7. Does 7 have any children? No, it doesn't. We pulled it out. It doesn't have any children. Fine. Our work at this level, level 3, is also done. Now let's move to level 4. So as we have gained a height, we will increase our height, right? Now let's check the nodes at this level, level 4. That is 8. Does 8 have any children? No, it doesn't. Let's see 2. Does 2 have any children? No, it doesn't. Now we have reached here after pulling all these nodes out, and we have finally saw that our queue is empty. That means we don't have any nodes left in our tree. That means our iteration is complete. Alright, and we have gained this much height. This is our maximum height, and we will return this. As simple as that. Now let's see our recursive approach. What we are going to do is we are going to perform a DFS, or a depth first search. Now what does DFS say? DFS says us to explore all the depths. Okay, it says us that hey, explore all the depths, and whichever of those is the deepest, you return that one. What does that mean? Let me repeat. We will start from here and we will go to every depth. This is one depth, this is one depth, this is one depth, this is one depth, right? Whichever is the deepest point that we will be able to achieve, that is going to be our answer. The magnitude of that depth, or the height from the root to that depth, right? That is going to be our answer. Now let's try. We are currently here, right? Our height is initially 0. Our height is initially 0. Okay. We are at root. Our height becomes 1. Okay. Let's go here. Our height becomes 2. Okay. Our maximum height that we have achieved is 2. Okay. Let's check the left child. Okay, it exists. We have gained a height 3. Okay, our maximum height is 3. Check here. Okay, we have no one. Go back. We have no one. Go back. Go back. We will check the right child. We have no one. Go back. Go back. Now we are again at here. Now we'll move this side. Okay, 1 plus 1 is 2. Okay, check left. 2 plus 1 is 3. Go to left. 3 plus 1 is 4. Okay, we have another height, new height, which is greater, and it's 4. Go down. No, we don't have anyone. Go back. See right. We don't have anyone. Go back. Go back. Check the right. Okay, we have something. Height increases to 4 again, but it's already 4. Okay, check left. There is nothing. Go back. Check right. There is nothing. Go back. Go back. Go back. Now let's check the right for 20. We come here. Height increases to 3. Okay, check left. No, we don't have anyone. Go back. Check right. No. Go back. Go back. Go back. Finally return. So what is the maximum height that we have achieved? It's 4, right? Now let's code it. We need something to keep track of our maximum height, right? Let's call it max height equals to 0. Why did we declare it globally? So that we don't need to pass it again and again in our functions, right? Okay, let's call our DFS at the root node. Height is currently 1. Okay, and after finally all the DFS and stuff, the work inside is done, we'll have our max height updated fully. Then we will return max height. Okay, now let's write our DFS. DFS, what are we going to pass? We are going to pass the node and the height, the current height. Now we need to have a base case, right? We need to stop our at some point we have to stop our recursion. What is it going to be? See, when I explained, what did I do? We came like this, we came like this, then we saw that we have nothing here, so we came back. Then we came to this side, we saw we have nothing here, so we came back again. So this nothingness is going to be our base case, that if we don't encounter anything, we will not perform anything. We will simply roll back from there itself. We will return, right? So if root is null, simply return. Otherwise what happens? Say we are here, we come here. What does that mean? We have gained a height, right? Say our height here was 1. We have gained a height here, isn't it? So we are going to increase our current height by 1 plus 1. Let's say this is our max height. We are going to increase our current height by 1. So let's increase our height plus plus. Now we need to update our max height also, right? Our height was initially, first it was 1 0, then it became 1. Now we have 2. We will update it to 2. Our height is 2 now. So let's update our max height equals to math.max comma our current height. Fine. Now what is our next task? We are supposed to go deeper, right? We are supposed to go deeper to our left. So let's call our DFS for our left area. What is the left area? Root.left. We pass in the height that we have achieved so far. It will go until it encounters a null. Then it will come back. Okay, then it will come to the next line. Now what are we supposed to do? When it has come back, we need to check our right also, right? So let's call our DFS for our right area as well, right subtree. We pass in our height, current height so far. We go this side, we encounter a null. Okay, if root is null, return. It returns. Okay, then from here it will again return. Finally it's here. Now we are supposed to check this side. Okay, so for this one we are going to come to our right. We are going to increase our height becomes 2. max height, we update our max height. Okay, from here we come to our left, it all goes all towards the bottom, then it goes back like this. Our DFS happens, and finally at the end, when we are done traversing all the nodes, we'll have our max height updated. Okay, and then we'll return our max height. Let's try to run it. Let's submit. Definitely works, 0 ms. Now what is the time complexity? The time complexity of our DFS is big O of n. Now what is n? N is the number of nodes present in our tree. Okay, that is usually what the time complexity of DFS is. What is the space complexity? We are not using any extra space, but our recursion uses a stack space. Okay, so we are going to have a stack space of recursive stack space of height. Our recursion will start here, then it will come here until it goes to the bottom. All these are at hold, right? All these are at hold. They all are waiting for answers. They are stored in a stack. Okay, now it got its answer. It will return its answer to its father, its parent. Now it will return its answer to its father, its parent. So this is the recursive stack space. This is actually what I am talking about. Like why does the height? This is the height, right? So this is the space complexity. I hope that's clear. So that was all about this problem. I hope all of you understood. Tried my best to explain it. Okay, you can move to the solutions and you can check different answers as well. Here is mine. You can go and upvote it. All right. So thank you very much. See you in the next video. Bye bye.